Okay, let's jump right into this explainer. Today, we're going to master the exact concepts, the specific definitions, and the key formulas you absolutely need to ace the solutions chapter on your board exams. I know. Chemistry can sometimes feel like this massive, overwhelming wall of text, but we are going to break it all down visually, step by step, so you can walk into that exam room with total confidence.
Now, you might be thinking concentration is just some dry math problem you solve on paper. But in the real world, it's literally a matter of life or death. Just look at fluoride in drinking water. At exactly 1 part per million, it's great. It prevents tooth decay. But if you bump that up just a tiny bit to 1.5 parts per million, it actually causes your teeth to become mottled and discolored. And at high concentrations, well, sodium fluoride is actively used as rat poison. So when we talk about solutions and concentration today, we're really talking about the exact rules that dictate how substances interact in the real world.
So, here's our agenda. We'll start with the basics of solutions, move into calculating concentration, dive into solubility and Henry's law, unpack Raoult's law, and wrap up with colligative properties.
All right, Section 1, the basics of solutions.
Board examiners are incredibly strict about terminology here. You can't just write down that a solution is things mixed together. No way. This right here is the precise definition you need. Solutions are homogeneous mixtures of 2 or more components. Now, homogeneous is the absolute magic word there. It means the composition and properties are perfectly uniform throughout the entire mixture. The component present in the largest quantity is your solvent, and it determines the physical state of the solution. Everything else you dissolve into it, those are your solutes.
And take a look at this. It brilliantly illustrates the different categories of solutions, which, by the way, examiners love to use for those tricky one-mark multiple-choice questions. Notice how the solvent is always the boss. It dictates the final state. Solvent is a gas, you get a gaseous solution, like air. Solvent is a liquid, you get a liquid solution. You can even have solid solutions, like copper dissolved in gold.
Moving right along to Section 2, calculating concentration.
You'll want to keep your variables straight here, because these formulas are the absolute engines for those heavy 3-mark numerical problems. You've got mass percentage, just mass of the component over total mass times 100. Volume percentage is the exact same concept, just swapping in volume. Then there's mass by volume, which is huge in medicine, measuring solute mass in 100 milliliters of solution. For super tiny trace quantities, we use parts per million. And finally, mole fraction, which is just the moles of your target component divided by the total moles. Simple, right? Now pay close attention to this next part. If you only remember one single thing from this entire explainer, make it this high-yield comparison. Molarity versus molality. Molarity, with an R, is moles of solute per liter of solution. Because it relies on volume, and volume expands or contracts with heat, molarity actually changes when the temperature changes. But molality, with an L, is moles of solute per kilogram of solvent. Since it relies strictly on mass, molality does not change with temperature. I'm telling you, this is a guaranteed board exam question. Mark it down.
Okay, Section 3, solubility and Henry's law. When figuring out what dissolves in what, the golden rule is like dissolves like. Polar solutes dissolve in polar solvents, and nonpolar solutes dissolve in nonpolar solvents. It all boils down to intermolecular interactions. This is exactly why everyday table salt dissolves beautifully in water, but something like naphthalene simply won't. They just don't have the matching intermolecular forces to interact. Now, if you keep dumping solute into a solvent, eventually it's going to stop dissolving. We call this a saturated solution. Think of it as a state of dynamic equilibrium, the exact point where no more solute can possibly be dissolved at that specific temperature and pressure. That maximum concentration, that is officially known as its solubility. But what happens to gases when we mess with the temperature? Well, the dissolution of a gas in a liquid is an exothermic process, meaning it releases heat. So if we follow Le Chatelier's principle, adding heat by raising the temperature forces the equilibrium to shift backward. The solubility actually drops. This is a massive conceptual question on the boards. It perfectly explains why aquatic life struggles so much in artificially warmed rivers. There's literally just less dissolved oxygen available for them to breathe. And what about pressure? For this, you need to memorize this exact phrasing. At a given temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas. This is Henry's law, and it's absolutely monumental. It governs everything, from how factories carbonate your favorite soda water under high pressure to the mechanics of biological respiration in your own lungs.
Moving to Section 4,
Raoult's law explained. For a solution made up of volatile liquids, the rule is incredibly clear. The partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in solution. This is the precise textbook wording of Raoult's law. Seriously, do not paraphrase this on your exam. Write it exactly as it appears here to lock in those marks.
Let's quickly look at the math behind that. For component 1, its partial pressure equals its pure vapor pressure, that's P1 naught, multiplied by its mole fraction, X1. Same exact logic applies for component 2. And the total pressure? It's simply the sum of those two partial pressures. These formulas define what we call an ideal solution, one that obeys Raoult's law perfectly across all concentrations.
Now here's where it gets really cool. Look at how these two fundamental chemical laws mathematically intersect. Both of them state that partial pressure is proportional to mole fraction, right? The only difference is the proportionality constant. In Henry's law, it's Kh. In Raoult's law, it's the pure vapor pressure, P1 naught. So Raoult's law is actually just a special case of Henry's law, where Kh becomes equal to P1 naught. Examiners absolutely love testing this specific relationship.
Finally, Section 5, Colligative Properties. Here's the core question for this section. What happens to a solvent's physical properties when you add a non-volatile solute, like sugar or salt? Think about it logically for a second. In a pure liquid, the entire surface is covered with solvent molecules ready to evaporate. But throw in a non-volatile solute, and those solute particles start taking up valuable space on the surface. Because less surface area is covered by the solvent, fewer solvent molecules can escape into vapor, which means the overall vapor pressure is automatically lowered. And that brings us to a huge board exam favorite. Write this definition down word for word. Colligative properties are properties of solutions which depend on the number of solute particles and are independent of their chemical identity. The phrase examiners are desperately hunting for is depend on the number of solute particles. Honestly, it doesn't matter if you drop in glucose or urea. The only thing that matters is how many particles are floating around in there.
There are 4 major colligative properties you need to be familiar with. 1. Relative lowering of vapor pressure. 2. Elevation of boiling point. 3. Depression of freezing point. And 4. Osmotic pressure. And the crazy thing is, all of these actually stem directly from that initial lowering of vapor pressure we just talked about. When vapor pressure drops, the solution needs more heat to boil, so the boiling point goes up. Similarly, the freezing point goes down.
Let's zoom in on osmotic pressure for a second, because it is highly testable. Osmosis is the natural flow of solvent molecules moving through a semipermeable membrane, going from the pure solvent side over into the solution side. Osmotic pressure is defined as the exact amount of extra pressure you have to apply on the solution side to halt that flow entirely. It's the pressure required to just stop the process in its tracks.
And the best part? These colligative properties aren't just textbook theory. They are highly practical laboratory tools used to physically weigh molecules. You can take the standard osmotic pressure formula and rearrange it to solve for M2, the molar mass. In the real world, this is a crucial method scientists use to find the molar masses of massive, complex molecules like proteins and polymers.
Well, we've covered a tremendous amount of ground today. But before we wrap up this explainer, I want to leave you with one final provocative question. If colligative properties depend strictly on the total particle count, what happens when ionic compounds, like potassium chloride, dissolve and physically split apart into multiple independent ions? 1 mole of KCl suddenly becomes 1 mole of potassium ions and 1 mole of chloride ions. How does that dissociation change the rules of the game? It has to do with something called the Van Hoff factor. I'll let you check your textbooks for that one. Keep studying and good luck on those boards.